Go. Try read loud though.
Number 5.
Yeah, please.
When a ball is thrown upwards, what is its acceleration on the trip up?
Oh, wow. What do you think the acceleration is while the ball's moving up? I'm going to write while moving up. What do you think? What is this acceleration from? Which planet?
Earth.
So the Earth's gravity, do you think Earth's gravity is changing depending on which way the ball is moving? So the Earth's gravity didn't, the acceleration due to gravity ain't going to change the whole time. So which way is it? Up or down? How much? What number? I think we did this. Yes, you got it. What is it? What number?
10 meters per second per second.
Yeah, and the actual number is 9.8, but we round it to 10 meters per second, which is the same thing as 9.8 meters per second squared, which is about 10 meters per second squared. And notice that it's down. What's the next question?
What is its acceleration on the trip down?
What do you think?
The same.
Okay, so the trip down, same. What's the next question?
What is the acceleration when the object is at its maximum height?
What do you think?
Because it's just there for a few seconds.
Just because the velocity is 0 at that moment, right? When an object's at the top, at its highest position, and it's in free fall, just because it's not moving, you think the acceleration's 0? Acceleration isn't the same as velocity.
It stays the same.
So at maximum height, and you'll notice from yesterday, our velocity graphs had a constant slope that never changed. So like yesterday we had a velocity graph that looked like that. So at that moment there, even though the velocity was 0, the acceleration was still negative 9.8 meters per second squared. Because that's the slope. So the slope was still negative 9.8, even though the velocity itself had a value of 0. So what we're saying is you can not be moving for a moment, but your velocity is still changing at the same rate it always was, which was the acceleration due to gravity. And if you dig deep in your mind, think about the Earth itself and the acceleration due to the Earth. Just because a ball stopped in the air, would the acceleration due to the Earth's gravity change all of a sudden? It's tricky. It has to do with thinking about how it's moving is different than how it's moving is changing at that moment. And this is exactly that example. The velocity is changing, but the velocity happens to be 0 at that moment. And that's what's so tricky. You guys cool?
So the acceleration would be the same.
What is it?
It's always the same. It's 9.8 meters per second squared.
And what you're going to find also is you could throw a ball sideways in the air. Okay? Just because something's moving sideways, do you think the acceleration's different? We just changed the velocity. We didn't change the acceleration. It's still an object in the air. It's still called a projectile. It's still called an object in free fall. That implies that the acceleration is the same. And the reason we're studying this now is because this is a classic example of constant acceleration. And we know what that acceleration is because it's an object in free fall.
So when does the acceleration ever change, or it doesn't?
Well, if it's in free fall, if it's an object in free fall, and if we ignore what? What do we have to ignore for this acceleration to be valid? Air resistance. And where do we have to be in the universe to get this acceleration due to the Earth's gravity? Where do we live?
We live on Earth.
What part of the Earth?
Ground.
Yeah, okay. So this is valid at Earth's surface. If we went to the moon, it's like a totally different acceleration because you're in a different gravity field. So at Earth's moon, why did I write at Earth's moon? Whoops, didn't mean to do that. So I didn't mean that. At Earth's surface. And a lot of people get all confused, right? They think, oh, the astronauts are floating, so their acceleration is like zero. Hell no. They're falling. Those homies that are floating in space are only 10 miles away from us. It's like 5,000 miles to the Earth's center. So they're just a little bit different than us. They're almost the same. They're in the Earth's gravity field. That's how they orbit the Earth. So their acceleration is almost identical to ours, and they're falling around the Earth. It looks like they're floating, but you'd float too if you like drove a car off a cliff. You'd float, right? Or you would go off a jump on a bike. You're in the air. You're in free fall. That's your acceleration. Or you just like get air on a skateboard. You're the same acceleration if you're in free fall and if you ignore air.
So,
And if you're near the Earth's surface. What?
no matter what acceleration, it will always be 9.8 for like falling.
If you're at or near the Earth's surface, and if you're ignoring air resistance.
Mr. Day, so if we were to have sketching the acceleration, it would be like this, right?
Yeah, you'd have a horizontal, so your velocity graph looks like that, and then your acceleration, that would be valid if you made down negative and up positive. So if up is positive, then your acceleration has to be negative because it's down towards the Earth's center, and you just have a horizontal line like you have there, and that line's at 9.8 meters per second squared.
So it's going down 9.8 meters per second.
Well, yeah, what part of the Earth do you think the acceleration points towards? The center of the Earth. Cool? Like the other side of the planet, something's going to fall towards us. But it's really towards the Earth's center.
Number 2 is asking like what does meters per second really measure? Just the object's acceleration.
Yeah, beautiful.
And then
Cool. We're at 7 minutes, so I'm gonna stop the video so people have this.